This presentation is based on the paper What Bugs Live in the Cloud, a study of 3,000 plus issues in cloud systems. It was authored by three different sets of authors from University of Chicago, University of Wisconsin, and Surya University. My name is Michael Mamet, group 13, and I'll be presenting this analysis of the paper as well as a summary of the paper for CS643 Cloud Computing, NJIT, summer 2016. The paper is the result, or documents the result, of a comprehensive study of development and deployment issues related to 6 popular and important cloud systems: Hadoop MapReduce, HDFS, which is the Hadoop file system, HBase, Cassandra, Zookeeper, and Flume. All of these are through Apache Foundation, which provided the authors with a general repository of developer documentation that they could use to study and analyze the bugs that were associated with cloud systems, these particular ones. They conducted a deep analysis of 3,655 vital issues affecting deployment. The study was conducted over the course of a year. However, it covered 21,399 issues submitted over a 3-year period between 2011 and 2014. The result of the study is the CBSDB, very significantly and very importantly, the Cloud Bug Study Database, which is the repository of the bug study, and the bug study was the largest of its type conducted as of the publication of the paper. Now, the question, of course, is what motivated the authors to conduct this detailed and comprehensive study. What was bothering the authors is that they felt that cloud systems are still not 100% dependable, despite the fact that they are more mature now, even though cloud systems are still relatively new. The contributing factors primarily are the fact that cloud systems are constantly being developed, rapid development, rapid deployment, new architectures. All these things can lead to the introduction of bugs as you rapidly develop and deploy. The other factor, of course, is that cloud systems are inherently parallel systems, and parallel systems are more complex than serial processing, and there's a lot of factors that can contribute to bugs. Distributed components, hardware, obviously that's a classical problem. User interaction, deployment scenarios, all these things can contribute to downtime. Now, the goal of the paper was to identify and classify bugs in cloud systems. Now, obviously we can't classify and quantify every single bug, but my view on it is that the authors were trying to more or less establish patterns as opposed to document every single bug. There are bugs that are unique to cloud systems. In other words, there are bugs that are inherently classical types of bugs, and then there's bugs that are unique to cloud systems, which we'll talk about. What bugs are only found in deployment, and then the authors are also particularly interested in identifying these bugs because they're not captured necessarily prior to deployment. The result, which is the CBSDB, is where all of this information is documented. The authors used existing issue repositories, bug reports, patches, developer discussions to identify the bugs, and the fact that everything, all the products are associated with Apache Foundation gave them essentially a centralized location to get this information. Now, for the purposes of the cloud bug study, the authors were interested really only in vital issues. So they filtered out vital issues from what they considered miscellaneous ones. For each of the issues, they used existing information provided by developers. They looked at patches in terms of what patches were trying to address specific bugs. They then categorized the vital issues by aspect, and we'll go through each of those, but essentially these aspects kind of break out into classical and those that are specific or unique to cloud systems. So the issues of reliability, performance, availability, security, those are all the classical kind of issues. But data consistency, scalability, topology, and quality of service, those kind of fall more into the unique areas related to cloud systems. Obviously, all systems are subject to hardware failures, disk memory, etc. different types of failures, which we'll discuss, stop, corrupt, and limp. But as far as software bugs, which is the interesting point of the discussion, because the general feeling is that hardware is one thing, but software should be the responsibility of the developers. The largest area of software bugs, which is logic, the authors don't actually address in this paper. They don't address logic or optimization for that matter. They focus on error handling, configuration, data race, hang in space, and load, and we'll discuss those. And then they define the implications of these bugs, meaning what happens as a result of these bugs. We have performance problems, obviously, associated with some failed operations, downtime, corruption. Those are the worst cases. And again, the CBSDB documents all of this. And the purpose of it is really to allow for in-depth analysis by developers as they develop future cloud systems. Now, my humble assessment of this paper is that the authors were not necessarily trying to discover every single bug, because it's not possible, because new bugs appear every single day. But rather, their major contribution is the identification of classes of bugs. Sometimes it's more important to identify a pattern than identify an actual problem, because it's the patterns that lead to the future problems. And to that end, the paper is quite successful. The authors study and classify very important problems that relate to cloud systems, and that's because cloud systems, or any systems, they have to be stable in order to be viable. A great concept, a great idea, if it's not stable, if it's not scalable, it's not going to be viable. And the CBSDB is a major and significant resource for cloud developers, because it gives them a central location that they can go to get these bugs and perform analysis on them. And that in itself is a major effort towards achieving the author's real goal, which is to improve quality and reliability in cloud systems. The study is not necessarily original in its approach, obviously, because bug classification is not something new, but it was the first and largest study of its kind for cloud systems. The other thing that is very interesting and compelling about the paper is the fact that the authors mention and describe real bugs. They give real examples in these actual software products. So it's very practical, and it's not just theoretical. They're not just saying, well, what if this and what if that. They're showing real problems. Now, as far as the findings of the research, the classical categories are still the dominant ones. So reliability, performance, availability, those are still the top categories. But the new things, data consistency, scalability, and topology, those are unique to cloud systems, and that's part of what gets identified here in this paper. They also identify what they call killer bugs, those that simultaneously affect multiple nodes or the entire cluster, cascade of failures. Now, that's a very important point, because no single point of failure is the goal, and we'll talk more about that. Hardware failures, obviously, still are going to be a contributing factor. Cannot always deal with hardware failures at the software level, even though we would like to. Software bugs, obviously, those are also contributing factors, and we'll discuss each of these individually. Now, in reading the paper, what struck me as the major finding was this concept of availability first, correctness second. Now, we all know that availability looks better than downtime, but the authors contend that in cloud system development, availability is favored over reliability and data consistency, and hence the types of bugs that are associated with reliability and data consistency. So the authors kind of make the case that cloud system developers need better tools, and they need to use those tools at different points so that they can catch any and all hardware and software problems, which is obviously would be ideal, because bugs are caused by different problems, not just one. You can have one condition in conjunction with another, and bugs can be complex. Now, the methodology that the authors employed, again, was to study a diverse set of system architectures, and so they chose the 6 popular cloud systems. Again, the reason that they chose them is they were all these specific ones are all hosted under Apache, so they had available to them issue repositories, which were highly organized, with issues submitted by developers and users. They had a lot of information associated with the issues in terms of time to resolve, when, priority, patch availability, etc. They broke up the bugs into 5 priorities classed as minor and major. The focus here is on the major, critical, and blocker, all considered to be vital. Major issues, the trivial and minor was not focused on by the paper. Major systems, again, system development and deployment problems. Minor are real bugs that are easy to fix. The authors all reviewed the issues together to determine if they were vital, and if so, they included them. If not, they skipped them. And they produced what they refer to as aspects, issue aspects, and implication of bug scope labels, which we'll discuss. Now, as far as the methodology and the classifications, again, we have issue types, the aspects, the scope of the bugs, whether they're hardware or software, and what the implications are. And we will discuss each of these in the presentation. Now, as I mentioned earlier, the authors were interested in studying practical bugs. So to ensure the validity of the bugs that they were studying, they reviewed each in at least 2 passes. If anything was ambiguous, they discussed it until they reached a conclusion. The information that was stored in CBSDB is in various formats, and the paper presents the issues by classification with both quantitative and qualitative findings, and various footnotes and hyperlinks. Now, as I mentioned earlier, the classical system problems are still the 3 largest categories, and they're discussed in detail under killer bugs, hardware, and software problems. The graph on the left shows the issue types, breaking them out by vital and miscellaneous. Again, the authors focus on vital issues. And the graph on the right is essentially a heat map showing the issue aspects, which are reliability, performance, availability, security, consistency, scalability, topology, and quality of service. Now, at this point, we'll go into each of the issue aspects in detail. So the first is data consistency. Now, data consistency in parallel systems means that all the nodes or replicas must agree on all the data values. Now, we can have buggy logic in essentially anything that touches data. So buggy logic in operation protocols can cause data inconsistency. So for example, any data that's deleted but that gets treated as though it's valid, that's considered, obviously, data inconsistency. So for example, the authors, in studying Cassandra, they found that Cassandra should fetch necessary key value replicas from multiple neighbors, depending on per key consistency level. But what they found is that a protocol bug that was inherent in the development of Cassandra fetched one replica from only its nearest neighbor, therefore leading to inconsistent data. Another case they found was cross-data center synchronization compression algorithm might fail to compress key values. The error is caught. This is an interesting case because they catch the error, but the operation continues. So sometimes we catch an error in software development, but the operation continues and we still wind up with inconsistent values. Another case they found was with HBase connection problems resulted in cloning of metadata, which is interesting. The metadata gets copied over, but not the actual data. So that's definitely a data inconsistency scenario. Concurrency, another issue when you have multiple processes and competing for shared resources, you could wind up with data races between read and write. The result being that you get older values written to cache, which is of course an inconsistent data scenario. Another case they found reordering of async messages and node failures together resulted in data inconsistencies. Another case, committed transactions in different nodes in Zookeeper wind up with different views. So all of these were types of data consistency bugs that they uncovered. Now the next issue aspect is scalability, which only accounts for 2% of cloud issues. So the question might be, well, is it really significant? The authors think that it is because they find it very interesting because it's very hard to find in small scale testing. I think that the parallel processing scalability is a major component of parallel processing. So anything that's associated with scalability is significant. Now, the authors identify the different root causes and the implications. Obviously, performance, downtime, and failure are all significant implications of not being able to scale well on a platform. Now, the authors then, in order to understand this specific category, they break it down into four axes of scale, which is cluster size, data size, load, and failure. So the first topic, cluster size, has to do with the anticipation of what a cluster size will be, in processing the protocol algorithm. But that's not perfect because, for example, in Cassandra, they have a scenario that they found where a node changes ring position, leads to a key range recalculation, and then what happens is if it's a large cluster with 100 to 300 nodes, it leads to what they call CPU explosion, where the live nodes start flapping, essentially, where they're extremely busy. And then the result of that is they need to restart the entire cluster. Another scenario they found was large-scale recommission of nodes in HDFS bogs down critical services. So they wind up migrating blocks and log messages and things like that. So scalability is a major issue, even though it accounts for only a small percentage. Now, in the big data era, cloud systems must anticipate large data sizes, but it's not always clear what exactly the limit of big data is. So the authors found cases, for example, in HBase, where it opens a big table. It does an inefficient table lookup, and the table lookup takes a very long time. So just trying to determine the size of the data then becomes a problem. Another example, logging. Obviously, logging can generate a lot of log records. The cleanup falls behind incoming requests, and that becomes a problem. HDFS, another example the authors found, the boot protocol may not scale with respect to commit log segments and blocks, internode reboot messages. All these things cause the cluster reboot to take too long. So the size of the data can affect scalability. Another issue that the authors uncovered was the scale of request load. So, for example, cloud systems cannot always, for example, serve large request loads. So, for example, in HDFS, you could have a scenario where we have thousands of small files being created by users, even though they're small files, but they're all being done in parallel. Another example, Cassandra, storm of deletions, meaning massive deletes come in, and because it's trying to service those deletes, winds up blocking other more important requests. Another scenario, HDFS, start writing a large job, kill it, and what happens is it results in least recovery that causes RPCs, remote procedure calls, to be dropped. Now, another major issue is scale of failure. So failure that's localized, failure that's contained is one thing, but if we have a large number of components failing all at once in a parallel system, we could have a scenario where the recovery is not prepared for that sort of failure. So, for example, MapReduce, a very large MapReduce job, 16,000 failed mappers. The authors found a case where it took 7 hours, to recover due to unoptimized communication in HDFS. Zookeeper, another scenario they found, 1,000 clients simultaneously disconnect due to network failures. We wind up with a session stampede, and that causes live clients to be disconnected. Now, the next issue is topology aspect. This is one of those that was identified as being unique to cloud systems. Now, there were several cases that the authors found where cloud systems do not work properly on some network topology. So, for example, in distributed systems where we have, for example, cross data center, so cross DC awareness, communication latency for example, could be a problem. So, for example, they found a case with Cassandra where it took 1 day for a hint delivery installed across DC deployment. Similarly, with HBase, they found cross DC replication requests go back and forth, ping-ponging infinitely. So these are topology bugs. Rack awareness, for example, they may have some operation protocols. For example, recovery may not necessarily be rack aware. So problems that are dependent specifically on topology. The case they found with map reduce, where it always assumes that the mapper node is a problem instead of the network. So it winds up rerunning the mapper in the same rack, and then wind up incorrectly blacklisting all the nodes. Another scenario, new layering architecture. Cloud architecture evolves, but the protocols don't keep up. Cluster topology, for example, and scale can change suddenly. The cloud system is not aware of it. It's not been brought up to date with it, and it can't handle it. So, for example, with Cassandra, they found with virtual nodes, they may still be at the mercy of protocols that assume physical node topology, even though they're using virtual nodes, and that results in scalability problems. Case they found with HDFS, node groups affect failover, balancing, replication, and migration. Now the next issue aspect is quality of service. Now this is, although only accounted for a small number of the problems that the authors studied, only 1%, it's a major issue because it's a fundamental requirement of distributed systems. The authors view it as an unsolved problem as opposed to a non-problem. Now they break out quality of service issues into two categories. The first one, which is horizontal intrasystem quality of service, essentially are issues or operations that affect other operations. Now developers can sometimes quickly fix these problems. However, sometimes you fix one thing and then you break something else. So, for example, they found a case, for example, with HDFS, where throttling at the stream level causes requests to queue up at the RPC layer. So the point is that you introduce one new threshold in one protocol, it could affect another. The second case they discuss is vertical cross-system quality of service, which is a major issue in cloud systems because, and the authors actually view this as the biggest challenge of quality of service, because they say, look, developers can only control their own systems, but cloud systems demand end-to-end quality of service. So, for example, you can only control your piece, but you can't necessarily control what somebody else is doing. So, for example, HBase developers, they raise questions about quality of service at HBase will be translated at HDFS or MapReduce layers. Some techniques are hard to enforce. For example, disk quality of service. You don't have any control necessarily developing software, but you don't know what sort of platform it's going to be deployed on. So the other thing the authors identify is a lack of control of quality of service accuracy. Now, by studying issues of large-scale systems, the authors identify what they call as killer bugs. And killer bugs are essentially bugs that simultaneously affect multiple nodes or even an entire cluster. The authors view this particular study as very important because the subject of, or the principle of, no single point of failure, according to the authors, has been preached extensively within, amongst the cloud developers. But what the authors essentially say is that while it's ideal, it's not necessarily yet a reality. So they discuss various different types of killer bugs. The first one they talk about is what's called a positive feedback loop. So for example, a failure occurs, it's detected, recovery starts, but then it winds up introducing more load and then hence more failures. So they found a case, for example, with Cassandra, where gossip traffic makes a cluster unstable, live nodes wind up becoming incorrectly declared dead, then they wind up adding more nodes, and then they wind up causing more gossip traffic. Another scenario the authors describe is what's called buggy failover. Now, the term no single point of failure means that we detect a failure and then we fail over. Well, that's fine as long as the failover works, but what if the failover code itself is buggy? So for example, a case they found with HBase was failover of an HBase metadata region doesn't work as expected. The entire cluster is affected. So what happens is then the whole cluster metadata winds up being rendered inaccessible. Another scenario they found with HDFS, failover to standby node breaks, and then all the data nodes become unreachable. Another case the authors discuss is repeated bugs after failover. So no single point of failure means resumption of a previously failed operation. Well, generally speaking, if the cause is hardware failure, then the software will handle it. But what if the problem is a software failure? So, for example, the authors describe a case of H-base region server failing due to mishandling of corrupt region files. So it fails over to another live region server, but then winds up rerunning the same code and also fails. And then it repeats this process until all the region servers go offline. The other thing about single point of failure is there's really a very small window of recovery. So single point of failure means that failover is ensured all the time. Well, what happens if, for example, failover is disabled because of operational tasks, meaning things that need to be done operationally? For example, in Zookeeper, dynamic cluster reconfiguration. Now, what happens if that disables the heartbeat process and then failover isn't detected? Another case the authors discuss is buggy startup code. Startup code fails, then winds up rendering machines unusable. So, for example, the authors found a case with Zookeeper where there's a process called leader election. If it's bug prone, then the Zookeeper cluster winds up without a leader. Obviously doesn't function correctly. Another case the authors discussed was distributed deadlock. Now, coordination deadlock, depending upon what the software is, can mean different things. In some cases in database processing, it could mean one process winds up being killed and the other one continues. But in this case, they're talking about where it's a silent hang. Each node waits for the other to progress, and nothing happens in the meantime. So, for example, in Cassandra, they say nodes may never enter a normal state because they continue gossiping. HDFS can wind up with a disk can hang on one node, and then it causes an entire write pipeline to hang. So that's a silent hang. In distributed systems, that's referred to as a distributed deadlock. Another thing the authors discuss is scalability and quality of service bugs. We discussed those, but the key point is that scalability and quality of service, those things can cause an entire cluster to hang. Now, the graphic on the bottom of the page shows heat maps of the correlation between the scope of killer bugs, meaning multiple nodes or a whole cluster, and hardware or software root causes. Now, a killer bug can be caused by multiple root causes. The number in each of these cells represents the bug count. Moving on to the next issue the authors address, which are hardware issues. The authors consider this particular study very important because they want to know what are the reasons why cloud systems can't always deal with well-known hardware failure modes. So, first one they discuss is what's called fail-stop, which is, of course, the cloud systems are equipped with various mechanisms to handle fail-stop failures. Now, this isn't always simple. It can wind up with interleaving events. You have a series of multiple failures, all occurring at the same time, not handled properly, leading to massive failure. Force the system into an unexpected state. They also make the point of saying that the coordination services, like, for example, Zookeeper and HBase, doesn't always help. The other issue that they bring up is corruption. Now, this is, of course, a major issue when you talk about corruption of data. Now, it's well known that hardware, writing intermediate results and things like that incorrectly can cause data to become corrupt. Now, that's the reason why we have something called checksums, end-to-end checksums. It's not a perfect solution because if all the copies are corrupted, then the checksum is useless. The other scenario that they bring up is what if the detection of corruption is correct, but the recovery doesn't work? So, for example, in HDFS, they talk about a scenario where HDFS accidentally removes healthy copies, but then retains the corrupt ones. So, in other words, they detect the corruption correctly, but they remove the wrong copies and keep the corruption. Another scenario, false alarms wind up marking healthy copies as corrupt, and then that winds up triggering a data recovery, but it's not even necessary because the data is actually healthy. Another hardware issue the authors address is what's called a limp node. That's where otherwise good hardware can wind up becoming what they refer to as limpware. So for example, HDFS, assuming disk IOs will finish, disk degrades, name nodes hang. Another scenario they discuss, memory card running at only 25% of normal speed, wind up with out-of-memory condition, backlogs, and HBase winds up crashing. I mean, these are all scenarios where you have hardware that's good, but it's not running at full capacity, and hence the system, the cloud system winds up suffering as a result. The next graphic, the graphic here at the bottom, shows hardware faults. The graphic on the left shows the distribution of software and hardware faults. 87% is software and 13% is hardware. The figure on the right shows the heat map of the correlation between the various different hardware types and the failure modes. Each cell contains a number, that's the bug count, and the authors say that if they see that a component dies without any explanation, they assume it's a node failure. The next area the authors discuss is software issues, which is broken up into several subcategories: error handling, configuration, data races, hang, space, and load. Now, as I had mentioned earlier, the paper does not address logic and optimization bugs, which are two huge categories. Logic is number one at 29%, because those are domain specific and they're not classified with the general bug types. So the authors focus on the general bug types. Now, the graphic here shows software faults and implications, figures A and B. So they show the breakdown of different software faults and the implications, and we'll discuss them in the next slides. Now, getting further into the specific software issues, the first one the authors address is error handling, which accounts for 18% of the software bugs in the study. That's the second largest category after the logic bugs. Now, error handling is necessary because both hardware and software can fail. However, introducing error handling means introducing more code and hence more complexity, which therein may introduce bugs just by introducing error handling. The authors discuss the scenario of error failure detection, which is not always perfect. Sometimes when we're programming, we incorrectly detect an error. Sometimes we correctly detect it, but then we ignore it. I have some experience in that area myself, doing database programming where we had both message handlers and error handlers. We could wind up trapping a message in the message handler, but then not effectively handling it, or say, for example, handling a message but not handling an error, or handling an error but not handling a message. The authors cite cases of HDFS network failure, for example, being treated as a disk failure, and that triggers a disk check storm. Or within HDFS, write pipeline, hard to detect, for example, which node is the problem. Within MapReduce, you could have a bad network between the mapper and the reducer, and that's marked as the map node's fault, when it's really the network. Another issue the authors cite is the dependency in cloud systems on timeouts. When you have async protocols, too short of a timeout can cause a false positive, too long can wind up in operations hanging. Another very important point the authors make is with regards to cross-system timeouts. So, for example, HDFS and HBase being dependent on each other or interacting with one another have different periods with which they would declare a node dead. HDFS after 10 minutes, but HBase after 30 minutes. So obviously that can lead to very undesirable outcome. Error propagation. Errors propagated to and handled by an upper layer. For example, HBase relies on HDFS to detect errors. If HDFS doesn't detect it, HBase hangs because it's relying on HDFS to detect the errors. Error handling, errors propagated to upper layers, assumes that there'll be proper failure handling. So, for example, sometimes if failure handling gets confused and doesn't know what to do, the authors cite an example of Cassandra node staying alive, even if the data is dead and the commit disk is alive. The next category the authors discuss of software issues is configuration, which accounts for 14% of the software bugs in the study, fourth largest category. The authors say that this has recently become a hot research topic. So one example is what's known as a wrong configuration. So for example, say for example during a software upgrade, so there may be a set of configuration parameters that are in place, and then during the upgrade those parameters wind up getting reset. That's one case of a wrong configuration. Software, for example, introducing new configuration parameters that wind up not being backward compatible. So for example, if you have scripts running and they are specifying some configuration option that's not backward compatible, could wind up with failures, and other undesirable outcomes. Configurations not being compatible with the operating system, or even specifying incorrect values. Any of these cases, incorrect configuration can wind up leading to data loss or corruption. A case the authors cite is with MapReduce, where we set the same working directory for multiple MapReduce jobs. So now they're all writing to the same physical directory, and then there's file collisions, and of course that could lead to a very undesirable result. Another thing that the authors discuss is multiple configurations. So this is a case where the end users want more control. I happen to be quite familiar with this from my own experience working for a software company years ago, where there was a very limited set of database configuration parameters, and the users wanted more configuration parameters, and the vendor wound up introducing more and more and more configuration parameters, and then of course making everything more complex because now there's more knobs to turn, and it adds more complexity. So the authors bring a case of HBase admin disables a specific option called WAL, assuming in-memory data will be flushed to disk, but HBase doesn't do so when this is disabled. The next software issue that the authors address is what's known as the data race, which accounts for 12% of the software bugs in the study. Now, this is a fundamental problem in concurrent software systems. We discussed data races briefly, but just to review, a data race is when we have two or more threads, and they're accessing generally the same memory at the same time. Usually one is reading, one is writing, but they're not locking, or they're not using mutual exclusion, and they wind up, that condition is what's known as a data race. So this is considered a major research topic. Now, cloud systems are subject to what we call local concurrency bugs, obviously, like all systems, but they're also subject to distributed concurrency bugs because it's parallel processing across multiple nodes. Sometimes it's attributed to the reordering of async messages. Distributed data races sometimes can, one process can fail, and then we get a data race that way. But regardless, they account for more than, distributed data races account for more than 50% of the data race bugs in the study. The next software issue that the authors address is the hang condition, which is 4% of software bugs in the study. We discussed deadlocks and the silent hang before, so hang issues are generally attributed within distributed systems to deadlock conditions. Cloud developers have a broader definition. So for example, if an operation is supposed to run fast but it runs long, within cloud systems that'll be considered a hang condition. Now the silent hangs we talked about, which are, for example, complex, large code base, overlooks hanging components. For example, the authors cite a couple of cases, MapReduce developers initially not deploying timeouts for hanging AMs. Another case, buggy heartbeat threads keep reporting good heartbeats, even though some worker threads are hanging. Another case, overlooked limp node. We talked about limp nodes, some protocols being overlooked. For example, a job downloads a large jar file over degraded network, no timeout. And then another case the authors cite is an unserved task. Nodes are alive, but the tasks stay in the queue forever. So, for example, that winds up with a deep data race and logic bugs preventing system failover. Example, in MapReduce, tasks get stuck, preventing tasks from being relaunched elsewhere. The next software issue the authors address is space, 4% of the software bugs in the study. So, for example, big data Big data involves big data cleanup. Old data may consume massive amounts of space. Think about error logs, commit logs, temporary outputs, all that takes up a lot of space, and it all needs to be cleaned up. Sometimes it has to be done manually by a system administrator. If they've got to do manual cleanups, it could lead to downtime, affecting performance, or being out of space or having insufficient space can affect performance. Insufficient space, we can wind up with jobs and queries writing a lot of data, not having enough space, and that could lead to failures. Jobs fail or hang mid-execution if there's not enough memory. So users may need to manually split up jobs. We could wind up with resource leaks, which is poor space management. For example, memory, socket file descriptor, any of these things. They can happen during recovery. For example, a socket not closed. Of course, this is an interesting subject that the authors bring up. Is they say, well, now leaks can occur in Java-based cloud systems. Now, obviously, we're not supposed to have memory leaks in Java. So, the authors will say, well, we're not supposed to have memory leaks. Well, really? I mean, the authors are saying, well, that's not actually true. We can wind up with memory leaks, even though they're Java-based cloud systems. So as a result, the developers decide, well, they'd rather go ahead and use C and do dynamic memory allocation, or Java byte buffer. Well, now they've decided to take it upon themselves to do the memory allocation, and guess what? They wind up with careless memory management, and then we wind up with more memory leaks. The next software issue the authors address is load, which is 4% of software bugs in the study. Result of cloud system load requests, obviously parallel computing, distributed processing. Load is a huge part of that. The authors cite, for example, garbage collection. Load-intensive systems make frequent memory requests, memory allocation, deallocation, and forces Java garbage collection to run frequently. And then they cite examples where it pauses 8 to 10 seconds per gig of heap, or minutes for huge memory, which is obviously unacceptable. They also cite an example of beyond limit. Cloud systems often try to service requests despite the load, meaning they're not able to measure capacity effectively, wind up with out-of-memory conditions or backlogs that can cause the system to fail. At that point, we wind up in a situation where you can't service any requests. Operational loads, requests and operational loads can hang up important operations. For example, error logging is important, but it generates disk I/O. So if we're doing too much error logging, we're generating disk I/O, we'll wind up downgrading other operations that are more important. At this point in the presentation, we've discussed the various different issue aspects: data consistency, scalability, topology, quality of service, etc. We've talked about the killer bugs, the various different hardware issues, software issues, again, error handling, configuration, data race, hang, space, and load. So now the question is, what are the implications of all of this? Now the research demonstrates the implications of hardware and software failures and breaks them out in terms of percentage, failed operations being the largest category, 42%, performance problems next in line at 23%, downtime at 18%, data loss, corruption, and stale data. So through the paper we see that bugs can be caused by many different hardware as well as software faults. The upshot to all of this is that building highly dependable cloud systems is for now a distant goal, and that's something that the authors state within the paper. But the point of the research and the benefit of it is to develop this CBS-DB, the Cloud Bug Study Database. Now there are other cases, other things that the Cloud Bug Study Database can be used for other than essentially a repository of bugs. My view on it is that, again, the individual bugs are less important necessarily than the trends or the patterns. So using the Cloud Bug Study Database, other sort of metrics can be produced. For example, which bugs took the longest time to resolve and were most commented on. This helps in the analysis when determining how much, what the effort would be to resolve this type of bug. Looking at the bugs and breaking them out, saying, okay, well, which ones were in the top 1% versus the top 10%. using the Cloud Bug Study Database, we can analyze the distribution of the software bug types. There's also per component analysis, meaning which components occur, which bug types within which components occur most frequently. And that gives developers the ability to further analyze how multiple cloud systems interact. And then there's bug evolution. For example, the authors cite a spike between mid-2011 and 2012 correlates to the Hadoop architecture changes, which is the introduction of Hadoop 2.0 and Yarn. The graphic on the top shows the MapReduce bug evolution, which again the authors correlate this to the spike in bugs between that period of January of 2011 and 2012. The bottom graph shows software bugs based upon time to resolve, config, hang, logic, etc., and the number of responses. The graph on the top of the page shows the correlation between hardware and software faults and the implications. So on the top we see the failure modes limp, corrupt, and stop. On the bottom we see the software faults load, space, hang, race, config, optimization, error handling, and logic. The two figures represent heat maps of the correlation between the implications and the hardware and software faults. On the bottom we have the top 10 problematic components, those with the highest count of vital issues, broken out in this case by Cassandra, by HBase, and by MapReduce. So in conclusion, to summarize, this paper presents the first bug study of cloud systems and offers new insights into cloud system problems. It introduces a wide range of intricate bugs, many of them classic, many of them unique to distributed systems. For example, scalability, topology, and killer bugs. This was very important research, primarily because cloud systems are relatively young. Now, the paper doesn't necessarily offer solutions. There are some suggestions made around some of the problems that are presented. But really, the solution to the problem, in my opinion, is in some sense the collection of the data and the identification of the bugs, because the target audience is really the developers. So the authors are not setting out to tell developers, okay, look, here's the best way for you to go about developing code. What they're doing is they're saying, okay, we're going to collect and correlate and offer a database with this information and make that available to developers. And then the cloud developers can use that to either, look at these individual bugs or use it as a comprehensive data store of bug patterns, because it's not possible to identify every single bug. But in my view, patterns are more important. And the bottom line of the presentation is that the goal of achieving stable and dependable cloud systems is brought that much closer as a result of the research presented in this paper, and that found in CBSDB. And I would like to thank you all for listening, and the paper, as you know, is posted online.